Arrays versus linked lists. This is one of the first things you learn in data structures. It is also one of the most misleading. The textbook says the linked list should win. On real hardware, the array wins almost every time.
Here is the situation. You have 10 million numbers, and you need to add them all up. You store them twice, once in an array, which is one block of memory, and once in a linked list, where each number sits in its own small object that points to the next one. Then you walk each one from the start and add every value. The array finishes in 0.53 seconds. The linked list takes 1.53 seconds, nearly 3 times slower. And here is the strange part. Both walks touch every element exactly once. Both are O of n. By the book, they should cost the same. They do not. So something is charging you, and Big O never mentioned it.
So, let us name the subject. This unit is about arrays, linked lists, and the memory layout that decides which one actually wins. Layout means one thing here, where your data physically sits in memory. 4 ideas explain the whole gap. Contiguity, which means elements sitting side by side at neighboring addresses. The cache line, the CPU never fetches one number, it fetches 64 bytes. The prefetcher, which is the part of the chip that guesses where you are going next. And pointer chasing, where you only learn the next address after reading the current node. A few things this is not. It is not about how a list grows when it runs out of room. It is not stack versus heap. And it is not Big O itself. Those are their own units.
Before any code, one picture. Imagine a library. On the left, 8 books sit in one unbroken row, on one shelf, in order. You reach in once and lift 5 of them out together. You already know where book 6 is. It is right next to book 5. So you can send someone ahead to fetch the next handful while you read. On the right, the same 8 books, but each one is on its own stand, spread across the whole building. Inside every book is a slip of paper that tells you where the next book is. Now you cannot walk to book 6 until you have read book 5, so nobody can be sent ahead. Every trip has to wait for the trip before it to finish. Same books, same number of reads. One side can be carried in handfuls and guessed ahead. The other cannot. That is the whole episode. Here are both structures in the smallest Python I can write. The array is a plain list of 10 million numbers. One block where slot I sits beside slot I plus 1. The linked list is a node class with 2 slots, val and next. I use double underscore slots so that each node is exactly 48 bytes, with nothing spare. Now look at the 2 walks. They look almost the same, but read the last line of each one. The array asks for slot I plus 1. That is an address the CPU can work out by itself before it has read anything at all. The linked list has to open the node first because the address of the next one is written inside it. That single difference is the whole episode. And notice that Big O cannot see it. Both of these are O of n. These were measured on the machine that recorded this video. Adding up 10 million numbers in the contiguous array, 0.53 seconds. The identical additions, held as linked nodes, 1.53 seconds. 2.9 times slower for exactly the same operation count. But here is the part that should really bother you. If I build the linked list so that the nodes happen to be allocated in order, it takes 0.74 seconds. Now I shuffle only where those nodes are allocated. Same class, same node count, the same walk. Nothing in the code changes at all, and it takes 1.53 seconds. 2.1 times slower for a change that no line of code can see. So let us look at where the data physically is. Think of memory as one long row of numbered addresses, with low addresses on the left. An array is one unbroken run of neighbors, 8 values, 8 cells, side by side. Now the important part. The CPU cannot fetch one number. The smallest thing it can pull out of memory is called a cache line, and on this machine, that is 64 bytes. So when you ask for the first value, the next 7 arrive with it, for free. That is one trip to memory, 64 bytes fetched, and 64 bytes useful, nothing wasted. And the chip can guess ahead very easily, because the next address is simply this one plus 8. Now the same 8 values as a linked list, same row of memory, but these nodes were allocated at different times.
so each one landed wherever there was room. Value 0 here, value 1 far over there, value 2 back here again. Each node holds the address of the next one, and those are the arrows. Every arrow means the same thing. Next. One hop, one direction. A singly linked list really does only point forwards. Now count the trips. Each node sits in a different 64-byte line, so 8 values now cost 8 fetches instead of 1. And each fetch brings back 48 bytes of node, while the value it holds is another object somewhere else again. Worst of all, the chip cannot guess ahead anymore. The next address is inside a node it has not read yet. Nothing here is wrong. This is a perfectly good linked list. It just turned one trip into 8 and took away the only clue the CPU had.
So what does a trip to memory actually cost? I measured this in C, with no interpreter in the way. Following one pointer while the data is in L1, the cache closest to the core, takes 1.26 nanoseconds. Following one pointer once the data is out in main memory takes 81.5 nanoseconds. That is 65 times slower. You will often hear that a cache miss costs about 100 times a hit. On this machine it is 65. The exact number moves from machine to machine. The point that never moves is that it is not a few percent. It is 2 orders of magnitude, and it is the only thing that separated those 2 walks.
But distance is only half of it. Here is the other half. When you walk memory in order, the chip watches you. It sees address 8, then 16, then 24, so it guesses 32 and fetches it before you ask. That is the prefetcher. Measured, walking in order costs 0.62 nanoseconds per element, and that number does not change when the data is 1 gigabyte. The data is already at the core by the time you want it, so you never wait. Chasing pointers is the opposite. The address of node 6 is written inside node 5, so the chip cannot even start fetching 6 until 5 has arrived. Measured, 81.5 nanoseconds per element. One trip at a time, and every trip waits. Same machine, same amount of data, the same number of reads. 0.62 nanoseconds against 81.5. That is more than a factor of 130, and not one extra operation was added to get it.
If you only believe one experiment from this video, make it this one. One list, 10 million numbers. I read every element and add it up, twice. The first time I go in ascending order, 0, 1, 2, 3. The second time I shuffle the order first. Now look carefully at what is identical. The same list, the same 10 million index reads, the same 10 million additions, the same loop. There is no linked list anywhere near this code. The only thing that changes is the order I ask for the elements in. In order, 44.4 nanoseconds per access. Shuffled, 265.8, 6 times slower. So it was never about nodes or pointers or objects being slow. It is about layout, and about whether the chip can guess where you are going next. So is the textbook wrong? No, it is answering a different question. Big O counts how many operations you do as the input grows. Comparisons, moves, index reads, additions. It is machine independent on purpose, and about growth it is completely right. Both of those walks really are O of n. But look at what it never counts. How far away each piece of data is. How many 64-byte fetches those operations need, whether the chip can guess the next address, and what one operation actually costs in nanoseconds. Big O tells you how the cost grows. It says nothing about what one step costs, and it quietly treats every step as if they all cost the same. On real hardware, they do not. 2 structures can share a complexity class and still be 65 times apart. Now let us be fair, because the textbook has a real case, inserting at the front. To put a value at the front of an array, every existing element has to shift up by 1 slot. To put it at the front of a linked list, you allocate 1 node and rewrite 1 pointer. So let us measure it. At 1,000 elements, the array insert costs 1,100 nanoseconds, and the linked list costs 196. At 1 million elements, the array insert costs 572,000 nanoseconds. It grew by a factor of 519. The linked list costs 243 nanoseconds. It barely moved at all. This is a real win, and it gets bigger as the data grows. When people say linked lists are good at inserts, this is what they mean. And they are right.
But here is the precondition that nobody quotes with it, that O of 1 is only true if you are already holding the node you want to insert after. If you have to find the position first, you have to walk there, and now both sides are O of n. But those two O of n are not the same animal. The array does one min move, which is one straight sweep through memory, and that is the most prefetch-friendly thing a CPU can do. The linked list does 500,000 dependent cache misses, one after another, each waiting for the last. So measured, inserting into the middle of 1,000,000 elements, the array takes 255 microseconds. The linked list takes 63 milliseconds. Same complexity class, 249 times apart. The famous O of 1 is real, but it is a statement about the splice, not about getting there.
So when should you reach for each one? Reach for contiguous when you iterate the whole thing and you do it often. When you index into it, data at I in one step at any size. And when memory matters, 8 bytes an element against 80 for nodes. That is very nearly every collection you have ever written, which is why it is the default in every language. Reach for a linked structure for work at the ends. Here, a dec beat list.insert at 0 by 477 times. For removing a node you already hold, which was 41 times faster than deleting by index. For references that must stay valid while the structure grows. I watched an array move 15 times as it grew. And for queues, schedulers, LRU caches, and the free lists inside memory allocators. All 4 of those are real, and notice what they have in common. They all need the node already in your hand.
Which is why your language has already decided for you. A Python list is a contiguous array of pointers. The values live elsewhere, but the pointers are neighbors, and the pointers are what you walk. Collections.deque is not a chain of single nodes. It is a linked list of blocks, so inside every block you are contiguous again. That is the practical hybrid, and it is why a deque wins at the ends without losing everything in the middle. Java ships linked list, and the man who wrote it has said in public that he never uses it. Arrow list is the default, and a NumPy array goes further still, raw values, with no per element object at all, 8 bytes each against 80 for nodes.
Here are 3 questions you will be asked almost word for word. First, both are O of n to traverse, so why is the linked list slower? Big O counts operations, not distance. The array is contiguous, so one 64-byte fetch brings 8 values. The list scatters, so each node is its own fetch, and each one waits for the last. Second, what is a cache line, and why should you care? It is the smallest thing a CPU can fetch from memory. You never read one number, you read the 64 bytes it happens to live in. Third, linked list insert is O of 1, so why is that not the whole story? Because it assumes you already hold the node. Notice that none of these are definitions. Every one of them is asking whether you know where the cost actually lives.
And 2 more that separate the answers. When would you genuinely choose a linked structure? Work at both ends, removing a node you already hold, references that must survive growth. And a full answer names the real one people use, a deque, which is blocks, not single nodes. Last one. A loop over a big collection is slow. What do you look at first? Ask where the data sits before you change the algorithm. Walk it in the order it is stored so that the prefetcher can run ahead. Prefer one contiguous block to many small scattered objects. And then measure. On this machine, the order alone was worth 6 times. If you can name the trade-off and then say what you would reach for instead, you have answered it. That was Unit 10, the missing CS degree, 1 unit at a time. If this filled in a gap, hit like and subscribe so that the next one finds you.